Okay, let's start the session. So, before I move into the actual question, so the following example needs some clarification. So, yesterday we consider this example: fx equals to x when we have 0 less than equals to x less than equals to 1 and 3 minus x 1 less than x less than equals to 2. So this is a function which satisfy the definition, satisfy the condition in the intermediate value theorem. That means what? That means f of 0, what is f of 0? 0, and f of 2 is equals to 1. So if we have any k in between 0 and 1, there will exist an element, there will exist a c in 0 to 2 such that f of c is equals to that number k. Okay? And obviously you can see that this function is not continuous at 1. So left hand limit and right hand limit, there are different. So they are not continuous at the point 1. So this function satisfies the definition, the condition given in the intermediate value theorem. But this function does not have the intermediate value property. The way we define the intermediate value property, this function does not have intermediate value property. What is intermediate value property? We said that if we have a function from AB to R, and if we consider any pair of x1, x2 in between A and B, and let's consider, let's say f of x1 not equals to f of x2, and k is a number in between f of x1 and f of x2, then there always exists an element. So there always exists an element c in belongs to x1 comma x2 such that f of c is equals to k. Okay, so every pair of points x1 and x2 for which f of x1 not equals to f of x2, if we choose a number k in between f of x1 and f of x2, okay, it might possible that f of x2 is greater than f of x1. Let me write out f of x2 comma f of x1. Then there will exist an element c in between x1 and x2 such that f of c equals to k. Now you can see that this function does not satisfy this property. Why? So consider x1 equals to half and x2 equals to 3 by 2. What is f of x1? It's half. And f of x2 is 3 minus 3 by 2. So 3 by 2 again. Now obviously you have a number like 1 by 2 less than 1 plus 1 by 3 less than 3 by 2, correct? Because 3 by 2 is nothing but 1 plus 1 by 2. So we'll choose the number 1 plus 1 by 3. Obviously it will be in between half comma 1 plus 3 by 2. What is that number? 4 by 3. Okay. So we have the 4k, our k is now 4 by 3. Now what is the pre-image of 4 by 3? Obviously there will be a pre-image of 4 by 3 because 4 by 3, no, it's not necessarily that it will have a pre-image. But k equals to, you have 4 by 3. So let's see what is the pre-image of 4 by 3. So obviously if we have an x or c in between 0 to 1, you cannot have 4 by 3 because 4 by 3 is greater than 1. So let's say if we have f of c is 4 by 3, then obviously c should be greater than 1 and therefore it is 3 minus C minus 4 by 3, and C is your 3 minus 4 by 3. So 9 minus 4, 5 by 3, and it is 5 by 3 is greater than 3 by 3. Correct. 10 greater than 9, so 5 by 3 is greater than 3 by 3. So you can see that this C equals to 5 by 3 does not belongs to this integral. So this proves that the function has no intermediate value property. Thank you, Taran. Sharan, okay. Sorry. He pointed out that thing. That this is a function which does not satisfy intermediate value, because today I said that if we have a function satisfied intermediate value property, then it cannot have a discontinuity of first kind. Okay, but that function has discontinuity of the first kind, because this function left hand limit like right hand limit both exist. Okay, so this other way to say that okay, this function cannot have intermediate value theorem, intermediate value property, because it has a discontinuity of first kind. Okay, now the question is, do we have an example of a function which is not continuous but have intermediate value property? Okay.
Because this 1 by 3 is like 1 by 200. So when you are applying f of c is
What is that one?
C, f of c equal to 3, how can we, because c may be like 1 by 2 3 by 2. So the function is,
so you have this in between 0 to 1. So let's say if we have a c in between 0 to 1, so this value will be just 4 by 3 is greater than 1. So you cannot have a number 4 by 3. Correct. What is the 4? A is your 4 by 3. So obviously this is greater than 1. So C cannot be a number in between 0 and 1, because it's mapping to x. So therefore it should be of this form. Okay, so I'm not proving that this function has intermediate value property, but this is an example. So f of x, okay, by the way, f is defined in between -1 to 1 to r. This is called topology sines r. So we have sine 1 by x. Okay, so topology sines r is little different, but it's like that. X not equals to 0. And 0 when x equals to 0. So this function has intermediate value property, but this function is not continuous at the point 0. This function has intermediate value property, but f is not continuous at x equals to 0. I suggest you to try to solve this problem, that this function has intermediate value property. Not continuous is easy to see. Okay. So this was from the last day's lecture. So in today's lecture, there are something I should clear out. Like when I discuss the types of discontinuity, I consider the left end point of the integral and then interior point of the integral. Okay. So some of you ask why we consider left end point of the integral and interior point separately, why not at the same time? Okay. So because for interior point, what we have, we consider both the right hand limit of the function and left hand limit of the function at the point fx, and depends on that we have classified types of discontinuity. Okay, but when you have a function which is not an interior point, so the thing is now not between left and right hand. It's like interior point or not an interior point. So if it is not an interior point, in that case we consider the left hand point, because interval means it's obviously should be either left or right, because in middle it will be interior. So for the left hand point, what we discussed, we don't have this idea of limit x tends to c plus. We only have the idea limit x tends to c fx. Does it exist or does not exist? If it exists, then we have different notion. If it does not exist, then we have whether it is bounded in some limited neighborhood or not, or it is unbounded in all neighborhood or not. So these are the things we discuss. So because another thing is that when we say, so I hope that it is, if you have a doubt, it's clear now that why we have to consider interior point and non-interior point like the left hand point or right hand point. It is because when you have the interior point, you can define many other things, which is restricted for this case only. Okay. Second thing is that the left end point. So left end point, it might possible you have this type of interval. Sorry. A comma B. Obviously, at the point A, function is not defined. Fine. But that means function has discontinuity. We are saying that the function has discontinuity at the point in that sense, because A is not in that interval. Okay. So in general, we don't say that if a function is not defined at that point, we are not bothered with whether it is discontinuous or continuous. But because we are considering, let's say, a function in the whole real line, okay, and then considering AB, and now we want to know, like in most of the cases, you'll find that like we have a function fx which is defined. It can be defined in whole real line. Now, inside of that, now we just consider open interval AB and want to know whether this function is continuous or discontinuous and no open interval. Obviously, if the point is not there, obviously it will be discontinuous at that for that interval. And now we are discussing what type of discontinuity we have. So if you are not comfortable with that fact that okay, this point is not there in that left in the interval, so we are not bothered with whether it is discontinuous at that point or not, it's fine. But let's say we can have this type of thing, then you might be thinking about, okay, now we have to discuss about the continuity of the function at that point. But if you look at the way we classify, everywhere, I mean, all these three different categories, we nowhere, I mean, it depends on whether the limit at that point exists, limit x tends to fx exists or does not exist. It's not that whether the function is defined at that point or does not define, it does not matter. Okay, you can still classify. Now, obviously, that's the way. That's why it's defined differently. Okay, it might look awkward, but now you have to think that the function is defined in the whole real line. And now, what about in the open interval? And what about the left hand point? The function is not a continuous function if it is not there. Now, what type of discontinuity we can think about? If it is there, then still you can discuss what type of discontinuity you have. So these are the things. I hope that it's still, if you have any doubt, we can discuss. But because it's just like why we are classifying defined things. It's not that any mathematical thing, but it's like we are defining this way. No sense. But if you look at the way we categorize, it's not violating any mathematical axioms. It's okay, it's fine. But how we are looking at, I mean, taking this, that's the important thing. I hope. Any question? It's clear. I mean, what I want to say, when you have left hand point, it might possible the function is defined at that point or not defined. But still, we have to consider. Okay, now we'll solve some problems. going on. Okay, just a minute. Let me. We go and solve exercise question given the tutorial sheet, but before that, we solve a little bit extra. I think 1 by x sine 1 by x we have discussed, correct? Okay, consider this example. Let fx equals to box x. 0 less than x less than 2. Okay. To discuss the type of discontinuity for this function. Very simple. So what is fx actually? In between given so 0 and 1 it is it's 0. So 0 when 0 less than x less than 1 and then 1 when 1 less than equals to x less than 2. Correct? So now what type of discontinuity you have? So it's a constant between 0 and 1. See, does not matter then. Between 1 and 2 you have to consider. So 1 is an interior point of the interval. So that means now whether left hand limit, right hand limit exists or not. What is the left hand limit? X tends to 1 minus fx. So can you tell us what will be the left hand limit? Because you are just young student, very young, student. Okay, what will be the left hand limit of this function as x tends to? So what is the value of fx? So when x tends to 1, but it's a 1 minus, that means what? So it's a neighborhood of 1, but it's a left hand neighborhood. That means x are less than 1. So when x is less than 1, what is fx? It is 0. So this, therefore this limit will be 0. And limit x tends to 1 plus, what will be fx? It will be 1 because now x is greater than 1. So it is 1. So you can see that left hand limit and right hand limit are different. So obviously this function has jump discontinuity and they exist finitely. So therefore, yes, so x equals to 0 is a point of jump. Oh, sorry. Yeah. It's a point of jump discontinuity of a. What is the jump, total jump of the function? How we define total jump? Upper minus lower. So total jump is, we define jf at the point 1 as f1 plus 0, that is the right hand limit minus so it's 1. Good. So next example. Okay, any is there any doubt? Timing, any question? Is it clear? I think for most of you is very clear. Okay, anyway. What about fx is sin x, not sin x, sin 1 by x when x not equals to 0, 0 when x equals to 0. So now this function is defined on whole real line. So what type of discontinuity you have? You have discontinuity at the point 0. That we have almost all of us very sure. So what type of discontinuity you have? Okay, by the way, left hand limit, right hand limit does not exist, correct? Okay, then lim in. Okay, so what is lim of fx as x tends to 0 plus, which is actually we are using this notation 0 plus 0 bar. What it would be? We already learned in the morning. If we consider a sequence of like, yeah, that sequence will work. 5 by 2, then 4 by 4n plus 5 by 2. So this will be 1. Okay, is it clear to everyone how it will work? Okay, what is the imp of apex? Or you have imp of 0 plus 0 is it is also going to be minus 1. And what will be 0 minus this? It's again going to be 1, and 0 minus 0 lower, it will be minus 1 again. Right? The same idea is the same. So that means here 4 exists and finitely. Okay. That means f is bounded in some neighborhood of 0. Okay. Actually, f is bounded in each neighborhood of 0 in this case because you have sine 1 by x function. So what type of discontinuity you have? Called oscillatory discontinuity. Okay. So or finite oscillatory discontinuity you can say as well. Okay. So x equals to 0 is a point of oscillatory discontinuity of A. When you have oscillatory discontinuity, what you calculate? Oscillation. So what is the oscillation of A at 0? We take the maximum of all this number, then minimum. What is the maximum? 1 and minimum? Minus 1. Oscillation is 2. Okay. Good. Okay. Let's say in this example, let's modify a little bit. Fx equals to mod of sine 1 by x. X not equals to 0. 0 when x is equals to 0. What will be f of 0 plus 0? But it will be 1 again. Supremum will be same. 0 plus 0 lower bar will be now. Now it would be 0, not the minus 1 because we have the mod value. So we have 0. And 0 minus 0 bar will be 1 and 0 minus 0 lower bar will be 0. What will be the oscillation? Maximum 1, minimum 0. So again, this is also a point of finite oscillatory discontinuity. And these are all second kind of discontinuity. When we have only removable and jump are they are called first kind of discontinuity or simple discontinuity.
So anything change if you put mod of 1 upon x?
Yeah, it will change. That limit infimum will change because whatever sequence you will consider, the value of f of xn cannot be a negative number because of mod.
You get the variable mod of 1 upon x.
Mod
of mod 1 upon x.
Sine of mod. Okay, 1 by mod x. Okay, so let's see. Fx equals to now sine 1 by mod x. When x not equals to 0, 0 when x equals to 0. So, what will change in this case? Whatever you consider the same sequence you will get. Okay. Is it or something different?
0 in the same way.
Yeah, it will approach 0 in the same way, but even odd term will not going to change. Like, so you will again going to get -1 in this case. So in this case, it will be similar to the first case. Because negative is possibility is there. Because the terms of the sequence does not matter. But the value of sign function matters. Okay. So in this case, you again get the first type of case. Like this case will get. Good question. Okay, obviously try to solve the same question using cos function or any other function. Okay, now let's say fx equals to x sine 1 by x. When x not equals to 0, 0 when x equals to 0. Okay. So is it a bounded function or unbounded? Whatever neighborhood of 0 we consider, it will be unbounded function. But let's calculate. Don't bother with much with bounded, unbounded right now, but think about what we can do with the sequences. What will be the supremum 0 tends to 0? So again, think about that. One term will give you 1, the sequence of all the 4n plus 1 pi by 2, and 1 by that will give you 1, and that 4n plus 1 pi by 2 will move towards. Okay, just no, I think it should be 1 by x, because otherwise it is its limit exists. Oh, I'm sorry. Yeah, for this function, the bounded function. What I will be limit x tends to 0, x sine 1 by x is 0, which is same as f of 0. So this function is continuous at the point 0. It's a bounded function. So I was also thinking why I am getting different, because it looks like x is bounded on 0 in the neighborhood of 0 as well as sine is bounded, so totally it should be bounded. Okay, so this is a function which is nowhere discontinuous, everywhere. So f is everywhere continuous. So you see, when we are discussing discontinuity, suddenly a continuous function comes, we think about it in terms of discontinuity. Okay. If x equals to 1 by x sine 1 by x. This is the answer I need to say. Now as x tends, when you move u towards 0, 1 by x become unbounded function. Okay. So smaller you get, 1 by x become larger. So this is an unbounded function everywhere in that neighborhood. Okay. Now what will be f of 0 plus 0? But supremum will be, so it will be like if you take a sequence of 4n plus 1 pi by 2 form, so sine will move towards 1, but the other part will move towards infinity. Is it clear what I am saying? So if you consider the sequence of this form, 1 by 4n plus 1 pi by 2, then f of xn will be what? 4n plus 1 pi by 2 into sine 4n plus 1 pi by 2. And you have 4n plus 1 pi by 2, because this part is 1, so this is moving towards infinity as n tends to infinity. Okay. So therefore this will be infinity. And similarly, if you consider this sequence, what sequence we need to consider to get a negative value? 1 by 2n plus 3. 4n plus 3? 4n plus 3 will not be okay. Okay. This will be, we have 4n plus 3 pi by 2 into sine 4n plus 3 into pi by 2, and this term will be negative. So negative 4n plus 3 pi by 2, and this will move towards minus infinity as n tends to infinity. So therefore f of 0 plus 0 lower bound is minus infinity. So as a point 0, what type of discontinuity we have for this function? It's an infinite oscillatory discontinuity at right of C. So this function has infinite oscillatory discontinuity at right of C. So f has an infinite oscillatory discontinuity at right of 0. C is 0 in this case. Because they are unequal. If both of them are infinity, then okay, it's fine. But they are unequal. Similarly, if you calculate the left hand limit at the point 0, you get the same thing, and you are also going to have infinite oscillatory discontinuity. Okay, next example of the 2 example you consider, then we will go to the tutorial. Fx equals to 1 by x when x not equals to 0, 0 when x equals to 0. So it's a bounded or unbounded function? Unbounded function in each neighborhood of 0. So what will be 0 plus 0 bar? It will be infinity, very easy to see. And f of 0 plus 0 lower bar, it will be a positive number, so it will be infinity again. And f of 0 minus 0 bar, it will be it's a negative value. What do they have? Think about the sequence moving towards 0, like 1 by m. Then you have a, then you will get the infinity. And now 0 minus 1 by m. What will you give? Minus infinity. This is minus infinity. What type of discontinuity we have in this case? 0, 0, we have infinite discontinuity. This is not oscillatory. And also, so in both right and left end points, right and left of 0, we have infinite discontinuity. So H has infinite discontinuity on both right and left of 0. Both right and left we have infinite oscillatory response. Whatever if you put the mod value, mod of 1 by mod of x. So 1 it would be infinity, but for the negative it will be infinity as well. Okay, so all will be infinity in that case. The minus infinity will be not there. Because whatever xn converges to 0, 1 by xn obviously converges to infinity. Yes. And now if we have the mod value, then we will not going to get the negative value. Okay, what about, so 1 by x square? Like now we have fx equals to, like mod you have now x square. Then again it is unbounded, and what will be 0 plus 0, like mod case, this will be same. 0 plus 0 will be infinity, 0 minus 0 will be, sorry, yeah, 0 minus 0 will be infinity, 0 plus 0 lower will be infinity, and 0, 0 is infinity. Correct, all will be infinity. Okay, one thing you observe that, I don't know whether you observe or not, because all are infinity, what we can say limit x tends to 0, 1 by x square is actually infinity. But, so this is the correct thing. But suppose you write limit x tends to 0, 1 by x equals to infinity, is it correct? No, it's incorrect. Because see that upper sum and lower sum are different. So it cannot have infinity over here. But limit x tends to 0 plus is infinity. This is incorrect, but limit x tends to 0 plus 1 by x is infinity. Limit x tends to 0 minus 1 by x is minus infinity. So this is correct, but this is incorrect. So I have seen many people to make this mistake. Their limit x tends to 0, 1 by x, they put it as infinity. Its limit does not exist at all. But that right hand limit, left hand limit exists. So, and they are good. Okay, last example I'll do from here, then we'll move to tutorial. Let's say if x equals to tan x. Why do you have the problem? Let's find it. This one? These two equal means the right hand limit is infinity. Because limit to at the point right, no, not this and this. So limit to at x tends to 0 plus is infinity. Limit in x tends to 0 plus infinity. So therefore, these two concludes limit limit x tends to 0 plus fx is infinity. And these two imply that limit x tends to 0 minus fx is infinity. Now because right hand limit and left hand limit are same, therefore this total limit is infinity. Yeah, so discontinuous is different thing, but the limit I am talking about. Yeah, now when we are discussing infinite discontinuity, then you have to say that whether it's right or left. Okay, if a function, like for this function what we got, we say that okay, because both are equal, so it has infinite discontinuity at right of 0. Now because these two are equal, it has an infinite discontinuity at left of 0. We say in that way. You can say that okay, because both, but in general we don't say that way, like, but we just say that it's right or left, infinite discontinuity of the function. Yeah, as I said, that this function has discontinuity as pi by 2 because it's not defined at the point pi by 2. But anyway, we just want to calculate what will be. So f has discontinuity. Actually, not only pi by 2. Yeah, so you will have to stay with, but let's say we only just do it at x equals to pi by 2. What is upper sum? Not upper sum, I mean lim cube of pi by 2 comma 0. Zero plus pi by 2 plus 0. That means what? Yeah, all sine tan cos. So pi by 2 you have. So plus 0 means just above pi by 2. So that means it is like near second quadrant. Sine is positive, cos is negative, so it's a negative type of thing. So when you are moving towards that pi by 2, you will get a negative. So this will be minus infinity. And similarly, this is also going to be negative infinity. Now when you have pi by 2 minus 0, now what quadrant you should think? It's the first quadrant. Both are positive. So it will be infinity, infinity. So that means what? These are equal, these are equal. This function has infinite discontinuity at the point of pi by 2. That function has right of pi by 2. So f has infinite discontinuity at the right of pi by 2 as well as at the left of pi by 2. But the obviously limit does not exist. This limit exists, right hand limit exists, left hand limit exists, but the total limit. So also you can say limit. If you write like that, limit extends to pi by 2 tan x. It will make mistake. They write this is as infinity. This is incorrect. Because left hand limit, right hand limit are different. Limit does not exist. But limit extends to pi by 2 tan x is minus infinity. Limit extends to pi by 2. My left hand limit is okay. I hope that it is clear more or less what we mean by infinity. I mean discontinuity as infinity, oscillatory discontinuity, as infinite oscillatory discontinuity, jump. I think it's clear. If you have still any question, okay, we discussed many other examples. Let's say question number 26. A function is defined on R by fx equals to x. X belongs to set of rational numbers 0 if x does not belong to set of all rational. That is x is irrational. Prove that f is continuous at 0 and f is discontinuous. It has discontinuity of second kind at every other point. So this function is only continuous at 0, but discontinuity of second kind at every other point. I'm writing this question. So here x is what? X if x belongs to Q. 0 if x does not belong to Q. Am I correct? This was the question. Oh. So first of all, show that this function has this continuity at the point 0. How to show it? Just take epsilon greater than 0. We need to calculate fx minus f of 0. So what is fx is possible? If x is a rational number, then it will be x and f of 0 is 0. So x minus 0, which is nothing but mod x if x belongs to Q. And what we have, if x is irrational, then 0 minus 0, it will be 0 if x does not belong to Q. So obviously that means what? What we have to choose as delta? Yeah, choose delta equals to epsilon. Then x minus 0 less than delta will obviously imply, this will together will imply that fx minus f of 0 is nothing but maximum value is mod of x, which is less than epsilon. Therefore, f is continuous at at 0. How to show that it is discontinuous at any other point? Let's say C be a point. Obviously, and C is not equals to 0. Yeah, sequence of rationals, then it will be Cn converges to C, and sequence of irrational 0 converges to C. So that is not possible. Got the idea? So you suppose you have Xn be a sequence of rationals that converge to C, then f of xn will be xn. Obviously, this will converge to C, but this C will be f of C if C is rational. But if C is irrational, okay. So if C is irrational, then it is not possible. Because C is not equals to 0, so it's not possible. You got that? So if it is rational, it is fine. But if C is irrational, then f of C will be equals to 0, and that is not equals to C. So this proves that f is discontinuous if C is an irrational. So this proves f is not continuous at C if C is an irrational number. Okay. But let's say now if you consider sequence of irrationals, xn be and okay, a sequence of irrationals that converge to C, then you can see that f of xn will be 0, which can only converge to 0, obviously not equals to f of C, whatever C will have. Okay. So this also proves that function is not continuous at the irrational point. Therefore, f is discontinuous at C. But this part is actually not needed, but anyhow, we did it to this to see in both cases, both the cases. So it is fine. Up to this point, it's fine that we prove that function has continuity only at the point 0. Okay. Now we have to show that it cannot be a continuity of first kind. That means what? Either limit x tends to 0 plus or 0 minus does not exist. But you can see that clearly it does not exist. Why? So let C belongs to R and C does not equals to 0, and because of this we already discussed. So if you consider the sequence of rational converges to the point C, so it is converges. So what f of x, it converges to C only. And but if we have a sequence of irrationals, it will converge to 0 basically. So that means you cannot have limit supremum, limit infimum at the point that they will be different because C is not equals to 0. So this since C is not equals to 0, that lim sup x tends to C plus fx cannot be limit x tends to C plus lim of fx. Therefore, limit x tends to C plus fx does not exist. Similarly, you can prove that. We don't need to prove that the other part, the link in the white C is fine. Is it clear why it is so? Because if you consider the sequence of rational, it will converge to the point C only. And if you consider the sequence of irrationals converges to the point C, so we have two possibilities. One I am considering a sequence of rationals, and another is sequence of irrationals. Corresponding to this, you have f of xn. If it is rational, then it will converge to C, and this C is not equal to 2. And if you have sequence of irrationals, then your f of yn will converge to 0. So that means anyway that limit cannot exist because limit supremum, limit infimum cannot be same thing because one is going towards C, another is going towards 0. Now we have to check whether C is positive, negative, depends on that you have supremum, infimum. But anyhow, you can see that they cannot be the same thing. Is it clear? Because if it is same for each sequence, it should map to exactly one point. But it's mapping two different points. So because of that, it does not exist. So this proves that A has this proves A has okay discontinuity of second kind at C because C is arbitrary, so at each point it has fine. Okay, next question. Okay, find the location and nature of the points of discontinuity of the following function. Just look at the function, write it down, then we discuss. It's easy, but you have to know how to do it. Fx is limit x n tends to infinity 1 plus sin pi x whole to the power n minus 1 by 1 plus sin pi x whole to the power n plus 1. Okay. We have to discuss it. So fx, what is the question number? 27. Okay. 27A. We have fx limit n tends to infinity 1 plus sine pi x whole to the power n minus 1 1 plus sine pi x whole to the power n plus 1, correct? You can see that it's well defined because you whatever value is a 1 plus something, so it cannot be 0. Now, one is just very simple. What is that? If x is some number, then this becomes very easy.
Not, this is not an integer.
No. First, let's say x is an integer. Then what will happen? So sin pi x will be 1/6. So let's say case 1. Yes. Let x be an integer. Then sin pi x is 0. Therefore, our whole fx is 0. So that means it is continuous at the point. But let's write, we'll see continuous of this further later. Because we are discussing on the whole real line, so it will depend on the line. We consider only on the integer. So fx is 0 when x is an integer. Case 2. Now, if you look at the line, we have 0, minus pi to pi. So if you go this way, you will find that here somehow we have the value 1 and then it is coming down. And this is a total 2 pi. So it's like so going up, down, up and down. So that means maximum value of the function over here is 1 and minimum value is minus 1 for this function. Maximum value is 0 for this function. Here maximum value is 1, minimum value is 0. Now we'll divide the whole line into this type of thing. How to divide this? Like we have 0 to pi, then we'll go again to pi unit. Like pi, then we have 2 pi, then we have 3 pi. So it will continue again this way. So in general, what we can do, we can divide the line in the following way. 2m minus 1 less than x less than 2m. This is one part. And then we have 2m plus 1 part. Like 2 pi, 3 pi. Next what will be happen? 4 pi. Next what will happen? 6 pi type of thing. Okay. And that's why we put 2m over here and then 2m plus 1 and then 2m minus 1. We put. So similarly in this direction we have minus pi then minus 2 pi. This part will be minus 2 pi, then minus 3 pi and so on. Okay. So it will repeat that way. The whole line will cover in this way. So when we have this part, like 2m to 2m plus 1, what we are getting? Maximum value 1 and minimum value 0. But when we have 2m minus 1 to 2m, what we are getting? Maximum value 0, minimum value minus 1. So let me write it down. So for any integer m, 2m less than x less than 2m plus 1 over here, when x is whenever x satisfies this inequality, we have 0 less than sin pi x less than 1, correct? Because 2m plus pi will come here. 2m, that's why I take 2m. So then what we need? 1 plus, correct? So 0 plus 1 less than 1 plus sine pi x less than 1 plus 1. So we have 1 less than 1 plus sine pi x less than 2. So then what is the value of this limit fx in that case? When you have something like that, if we increase it as n tends to infinity, what will happen? So now you see that 1 plus sine pi x is greater than 1. So this implies that 1 by 1 plus sine pi x is less than 1. Fine? So therefore fx, for that x, when x is in between this, your limit n tends to infinity 1 plus sine pi x whole to the power n minus 1 by 1 plus sine pi x whole to the power n plus 1 is same as limit n tends to infinity 1 minus 1 by 1 plus sine pi x whole to the power n by 1 plus 1 by sine pi x whole to the power n, and because 1 by this is less than 1, so this moves towards 0, 0, ultimately it will be equal to 1 in this case. Right? Okay. Is it clear? Okay. What about the other case, 2m minus 1 less than x less than 2m? What will be the limit? Tell me. Minus 1 less than pi x less than 0, then? So, whenever 2m minus 1 less than x less than 2m, our minus sign value will be in between this. This implies 0 less than 1 plus sine pi x less than 1. Sine pi x is already in between the number between 0 and 1. So what is fx in that case? Limit n tends to infinity 1 plus sine pi x whole to the power n minus 1 by 1 plus sine pi x whole to the power n plus 1. It is, this part will be 0, this part will be 0 because it's less than 1, we have minus 1. In this case, you get minus 1. So what are the values we are getting therefore? Fx equals to 0 if x of the form x is an integer. Actually, we will put all the integers. Okay, x is an integer. 1 if 2m less than x less than 2m plus 1, where a belongs to z. Minus 1 if 2m minus 1 less than x less than 2m, n belongs to z. Correct? This is the actual function. It's given in a complicated form, but the function is like this. Now, why do you have the discontinuities? Only at integer points. So this function has discontinuity only at integer. What type of discontinuity you have? Jump discontinuity. Okay. Because whatever integer you consider, you have the jump discontinuity. So f has jump discontinuity at each integer point. Any question from the online participant? No. Fine. Is it okay? Okay, let's go to the next question. Okay, I'll solve B, C, I'll leave to you. Then I'll solve the question number 28. I don't know whether I get the time to solve questions. Okay, so B, okay, let's see. Let me discuss B little bit, then we'll discuss question number 28. Okay, limit n tends to infinity. Please write down the question, then we'll discuss. Limit n tends to infinity, limit t tends to 0. Sine square n factorial pi x by sine square n factorial pi x plus b. (27b). What is the question? Limit fx, limit n tends to infinity, limit t tends to 0, sine square n factorial pi x by sine square n factorial pi x plus b. Is this the question? Now see that if x is a rational number, then for sufficiently large a value of n, but this value will become, we have n factorial. So, like let's say it's a rational number p by q. So when you have any number n greater than q, what will happen? It will cancel out that q and you have integer multiple of pi. So that value will be 0. So you see that if x is a rational number, it's a rational, then for a sufficiently large n factorial pi x will be an integer multiple of pi. Hence, sine of n factorial pi x will be 0. Therefore, for fx will be 0.
When we say this one, because when we apply limit t, then only we get one only. Then apply limit n tends to infinity 1. Then one we get.
No, like sine you cannot cancel 0 this. If sine square is 0, 0 by 0 is not equals to 1. If you take limit t tends to 0, so then you cannot cancel. Because if it is become 0, then you cannot cancel. Otherwise, obviously you can do. Now we will do that. Okay, that means what? Rather, he said that if x is a irrational number, then that is not equals to 0. It cannot be 0. So we can now take limit t tends to 0 and cancel out, it will become 1. That's your case. Next case is like that. Yes. If x is an irrational number, then sine n factorial pi x is not equals to 0. It cannot be 0. So hence limit, therefore fx will be limit n tends to infinity, t tends to 0, this will be sine square n factorial pi x by sine square n factorial pi x, cancel out, you will have 1. So ultimately, what is the function we are taking over here? So therefore, our fx is 0 if x belongs to rational, 1 if x does not belong to rational. This function has discontinuity at every point. So there will be no point where a function is continuous. So and each point it has what type of discontinuity? Yeah. So discontinuity of second kind, because you cannot have that limit 0 plus or at what point you consider does not exist. So A has discontinuity of second kind at each real number. But is it oscillatory or infinite discontinuity? It's a bounded, correct. Whatever number you consider, either you get the value 1 or 0. So it's a bounded. So obviously you will get the oscillatory discontinuity. Second kind is fine, but more specifically, oscillatory, finite oscillatory. Is it fine? Okay, question number 28. So it is a function defined on 0, 1 by f of 0 is 1, and for each rational number of the form p by q, we have 1 by q form. And 0 if it is an irrational number. You have to prove that f is continuous at every irrational point and discontinuous at every rational point. Okay, first of all, show that it is discontinuous at every rational point. How to show it? Use sequential criteria. So if you consider a rational number, you have of the form p by q, you have the value 1 by q. Let's say you have a sequence converges to that, sequence of irrational converges to that. So obviously, because that's a rational number, the sequence of irrational will be 0, that cannot converge to a finite rational number. Therefore, it's obviously discontinuous at every rational point in 0, even at 0. So that part is very easy. That is continuous at every rational point. I am not doing it. Consider the sequence of irrationals which converges to that particular rational point you are choosing. Then you can clearly see that it's violating sequential criteria, so it's continuous at that. Okay, now we have to prove that the function is continuous at every irrational point. That's the main part of the story. 1 by q if x is p by q, 0 if x does not belong to q. So if x is f of 0 is 0, 0 was 0, correct? Now 1. What is it was given 1. And f of p by q is 1 by q. Obviously, GCD of p q is 1, and f of x, otherwise f of x is 0. Otherwise, let epsilon greater than 0. We'll use epsilon later definition. Be given. So by Archimedean property, there will exist a K such that, so then there exists a K belongs to natural number. This is by Archimedean property such that 1 by K is less than epsilon. One thing you observe that if you have a number n greater than K, then 1 by n obviously less than 1 by K and it will be less than epsilon. Okay. Now we are going to use a fact that there are only finitely many rational number with denominator less than or equals to K. Most of the rational numbers are greater than or equals to K. Why it is so? You can write like that. 1 by 1. Okay. Then you have 1 by 2, 2 by 2, 1 by 3, then 2 by 3, 3 by 3. And you can calculate that in this way. If you sort it out this way, you will get that there are, so the claim is that, so we are using this as a fact, there are only finitely many rational P by Q such that Q is less than or equals to K. This is a fact we are using in this way. GCD of P by Q, PQ is also important. Otherwise, so this part will not come in that scenario. This part will not come in that scenario. And then you can count it. Like this 1 by Q, 2 by Q in this way, Q minus 1 by Q. Just delete all those. We have GCD greater than 1. Okay. So there are only finitely many rationals P by Q such that Q less than or equals to 1. Now what? Let's say we have a irrational number. Okay. Let C belongs to 0, 1 be an irrational number. Because there are only finitely many points. No, only finitely many will have because of the GCD. GCD is 1, so we cannot have more than that. So you can later sort it out that way. Okay, so calculate that later. That's how you have only finitely. Okay, C belongs to 0 and B an irrational number. Then what? Then there exists a delta greater than 0 such that C minus delta, comma C plus delta contains no rational P by Q with Q is less than or equals to K. So we can do it. Because there are only finitely many rationals there, you can always get a integral which will not going to contain any of that finite numbers. So next one, for this integral, so let x belongs to C minus delta, comma C plus delta. If we have fx minus f of C, we have, now what are the possibilities? If fx is an irrational number, then it will be 0 minus 0. 0 minus 0 if x is irrational. Whatever the other case, whatever the case other, because it cannot contain, it does not contain any rational of the form P by Q where the denominator Q is less than k less than equals to k. So whatever value that it's of the form p by q, where q obviously greater than k. So therefore this number, whatever number you will get, let's say that number is n. Okay, what we will write is just write less than 1 by k. Whatever number you will get, for which that value is obviously less than 1 by k. If x is rational, actually in both cases you have the value less than 1 by k. Okay, so let me write it down in this following. It's better to, because we are writing the definition. It's of the 1 by n form, rational of the form m by n, and to GCD of mn1 and n is greater than k. In all cases, we see that our fx minus f of c is less than 1 by k, therefore less than its value, for all x belongs to c minus delta comma c plus delta. So this proves that function is continuous at the point. So, 330 correct? Or 345? 330. And that's all. Otherwise, I'll try to put something else. Any question from this continuity part? Any question from the online participant? Oh, by the way, I did not touch this type of question at all. Okay, because we have little time. Let me discuss a little bit. Okay, very quickly, we will discuss question number 22. These are the questions especially using intermediate value 12. Is there any non-constant continuous function having only irrational values? No, why not? Because if you have non-zero function, then so 1x1 you will have a non-zero value, and some other point you have the zero values, let's say, and then that between that two number you have rational, and by intermediate value theorem you should assume that value. Okay. So therefore you cannot have a non-constant continuous function that assume only irrational value. Is it clear? Yeah, that we use, but we did not use the property of connectedness. We just use this. Yeah, actually connectedness you can prove using intermediate value theorem. Vice versa. Yeah, that property we can use. Because we have learned something, now we can come down and say, okay. Okay, question number 23. Suppose a function maps a Cauchy sequence to a convergent sequence. So verify if A is continuous. Function on R maps Cauchy sequence to a convergent sequence. Verify if A is continuous on whole of R. Okay. So continuous means what? Let's see be a point. We have a convergent sequence to that point. Now convergent sequence is Cauchy sequence, and Cauchy sequence map to here in this case is a convergent sequence. So yeah, Cauchy map convergence sequence. So that means a convergence sequence maps to a convergence sequence. Now your task is to show that you get the same limit as f of c. You cannot have different limits. That's the idea, but it will be. Whatever Cauchy continuous is simple. If it is Cauchy, it will be convergent and then therefore Cauchy. Uniformly continuous, that you have to check. You are trying to find examples where it is not so. And that it's mapped Cauchy sequence to a convergent sequence. It will not be because there are some functions like let's say x square, f of x from R to R is x square, but it is not a uniformly continuous function on R, but it will map Cauchy sequence to Cauchy sequence. And because Cauchy sequence in real line is convergent, so it will map a Cauchy sequence to a convergent sequence. So this condition is given, then it will be continuous, Cauchy continuous, but not uniformly continuous. Example is f of x is 6. What about the question number 24? If f is a function, assume only rational values, and f of half is half, prove that f of x equals to half for all x. So it will be a constant function. If it assume only rational values, it's again same type of idea, but you have left zero light open, so you cannot directly apply intermediate value theorem over there. Yeah, intermediate continuity is there and it also closed and bounded intervals. Here we have left closed but right open. You have to prove it is a constant function. So suppose there is a point where it is not equal to half. That point may be less than half or greater than half. If it is less than half, consider only diagonal interval. So let's say f of x1 is not equal to half. Now either x1 will be less than half or x1 will be greater than half. If x1 is less than half, consider the function x1 comma half. It only assumes rational values. That is not possible unless the function is a constant function. Okay. So that will prove that, but f of half is half. So the only possibility is that f of x1 is half, or you can say that it's a contradiction or anything like that. Similarly, if x1 is greater than half, consider half to x1. Okay, and again you use the fact that it's assume only rational values. So that implies that function should be a constant function. So from there you get the contradiction as well. Okay. That means no such x1 will exist. Is it clear? Just you need to consider this good. What about the question number 25? Continuous on 0, 2 and f of 0 is f of 2. Prove that there exists at least one point C in 0, 1 shall exist in this question. What shall we do? We have to construct a function for which it will be. What will be that function? What function shall we consider so that we can apply that probability of intermediate value theorem? Consider a function hx equals to fx minus fx plus 1. That will be a continuous function, and from there it is intermediate value theorem. Whatever actual intermediate value theorem you have to use. Okay. Okay, you have to consider function in between 0 and 1, not in between 0 to 2, because x plus 1 you are considering. So that will overload you. That's all. Any question? Okay, next session will start again after 15 minutes. Okay, any question from online participant? Okay, then we're concluding this session.
We shall resume now. It's audible. Means you can hear it. Huh? No, no. Can you hear clearly? Right. Yeah. Can you? Fine. Okay. So we'll continue from tutorial sheets. So uh, yeah, let us try to do more of the tutorial problems today. So if G mod Z, G is cyclic, then G is abelian. We did that today. So that's over. Tutorial one, I think many of the problems are already over. Some of them are just theorems which we proved. Yeah, some of those problems are especially useful for these exam kind of questions. For example, problem 8. Prove that for any. So maybe we just note the result. So if you have any k in Zn, so when I write Zn, I mean set under modulo n, it forms an additive. I mean, it forms an abelian group, as you know. In fact, a cyclic group generated by 1. Okay. So this is Z mod n Z. Because in that case, you would consider the elements as equivalence classes or cosets, right? Same thing. I'll use Z in simple. So, but in this, the cyclic subgroup generated by K, for K, this is equal to cyclic subgroup generated by D, where D is the GCD of K and N. I think you know how to do this. Okay, D divides K implies subgroup generated by K is contained in subgroup generated by D. Okay. Then okay, one way would be if you have the same cardinality, then they have to be equal. Okay, can you show that they have the same cardinality? From K to D? I mean, angular bracket K to bracket D? Okay. How do you prove that every subgroup of a cyclic group is cyclic? So you have some cyclic group generated by say X. Okay. Use multiplicative notation only for now. So you have subgroup generated by X, group generated by X, and H is a subgroup of this group. H is a subgroup of G. How do you prove? What is the first step in that? H is also cyclic. That special. What is the generator? What is the generator of H? That is the question basically. Which number? You no. Hmm. I know that G can be written as X power something. That's okay. So every element of H is also X power something. But I want to say every element of H is one particular element power something. Not like maybe H consists of say X power 5 and X power 7 and X power 9. Maybe this is H, right? Of course, it's not possible. Maybe this is not generated by a single element of H. Correct. These are all generated by elements of G, but they are not generated by any element here. Correct. I mean, unless you have some particular number. So, how do you get the generator? Smallest positive integer, right? Yeah. So let m be the smallest, least, such that x power m is there in H. You know, every element of H is of the form x power something. So let m be the smallest such positive one. Okay. And the claim is that this will generate. Okay. So can you use that here? So in this case, you don't have to say something. Say let you can say let p be the smallest such that it's an element of that. Then what? And what must be true? Huh. That is true, but like, how do you get the GCD? How do you get? So obviously, we want to show that D is equal to GCD. How do you get that? Maybe I will say D prime. Okay, so because D is already fixed here in the statement, so I'll take that D. Just take D prime. We want to show that D prime is D only. How to do that? D prime divides what? Okay, so it is equal to some multiple of K. Some multiple, not every. Okay, fine. Yeah. So yeah, correct. That implies that P prime is equal to some m k modulo n. Okay, just to remind you that. Okay, I'll just write modulo modulo n. Yeah, modulo n. Okay. That is true for some m. Or z, some I mean z is enough. I'll just write z. Yeah, okay, fine. D is a multiple of k. That's fine. Modulo n. Is that what we want? Yes, you have to use division algorithm, right? Here, again, here also, how do you alternate? Whatever element you take, it will be generated by this division algorithm. You take any other x power n, then you take n divided by m, but the quotient can be in the form. Write n as, because this is the least one, so you can write n as qm plus, and then you show the by minimality of time, showing that x for r must also be there. And similarly, here what we do, you take, in fact, yeah, k is the smallest positive one, right? Generally, k is yeah. In fact, k is from here, so k is positive also when you take the representation. So k is positive also. So if you take k itself as somewhat something, say q d plus r, or try dividing by d. Okay, right. Is it right? Why does d divide k? Oh, okay. Sorry. Again, I mean this one, not the one element. Sorry, we have to show that. Okay. So I have to show that. I'm sorry. So take d as that one. So k is equal to d prime plus r. Fine. Then again, same argument. R must be what? R must be 0. Right. Is equal to 0. So k is equal of d prime. Yeah, k is a multiple of d prime. Can you say it is the smallest multiple of other? D prime is the greatest one, right? Right. So r equal to 0 by minimality. Fine. I mean, this is here. I'm not writing this here. So because d r can be written as k minus 2 d prime. K and d prime are there in this one in the subgroup. So therefore r is that. So since d prime is r is less than d prime, and d prime is the smallest one by assumption, positive in the subgroup. So this must be 0. Okay. So we get k is in fact equal to qd prime. Okay. D prime divides n is what I want. I'm also missing something here. Sorry. Yeah. Hold on. Actually, what did it state here? K is equal to D. No, no. I think I've misstated the result. I'm sorry. Is it D? No, that's correct. The order would be, order of K would be n divided by GCD of Kn. Yeah, order of K would be that's correct. So this is GCD. Okay. The other, I was thinking that I got it wrong. Yeah. Order of K divided by GCD. In fact, the subgroup is this. Okay. Yeah. If you want to show that D prime divides n. Yes. Hmm. Yeah. Okay. Yeah, fine. So D must divide D prime is true because D is the GCD. That is correct. D prime divides D, no? D prime divides D, greatest common divisor. Sorry. So we get D prime divides D. Okay. Okay. So we want to get one more thing. So this is okay. So the other thing we get is maybe D divides MK. Okay. 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 Correct. Yes. I forgot to use the fact that D prime is in MK. D prime is in MK just tells you that D prime multiple of K. D divides K. D prime. Completely forgot. Yeah. This is of course true. So yeah. Yes. Any questions? D is in that subgroup generated by K. So D prime is equal to MK. Okay. So D divides D prime. Well, that is also okay, but we have not proved that. We have not yet proved that the subgroup is that. This is okay. Now you need to. Greatest common divisor. Okay, okay. D prime divides N. Yes. Greatest common divisor. Sorry, D prime divides N is missing still, right? So okay. Let me actually do this through. 1 minute. Then tell me. Oh, right, right. Yes. Okay. T is equal to. Okay. Nm Nm plus KL. Okay. Since it is the GCD. Okay. Yeah. Based identity. So T is equal to Nm plus KL for some integers N and L. Okay. Fine. D prime is there in this one. What? Okay. D prime belongs to subgroup generated by D because I mean, I'm asking. Right, right. Okay, fine. Yeah, D prime belongs to this. Fine. Okay. D prime is equal to some. Okay, something where A is A. Okay, fine. K, correct? Modulo n, okay. Modulo n, it goes to 0. Second term is the modulo of K. This, what are you saying? What is the definition of D prime? Some element of, yeah. Okay, are you taking the same definition of D prime? Oh, okay. You're losing this part. Okay, fine. I got it. So fine. So you have taken D prime to be some element. Okay. Now I understood. Yes. So that's fine. Then when yes. So is equal to AKL. Then so okay. Fine. Yeah, correct. Yes, you're right. Business identity proof, you know. This do you know the proof? It is very simple because we already discussed it. That's why. So you take. So in this case, you're talking about GCD of n, right? So again, we know that Z is cyclic. Z is cyclic. So take n and k in Z. A subgroup generated by n and k. It will be cyclic, correct? What will be its generator? Because Z is cyclic, this must be cyclic. What will be its generator? If you the proof of what we discussed before. It will be GCD of nk. The cyclic subgroup generated by n and k will have generator GCD of nk. That proves this. So what is meant by cyclic what is meant by subgroup generated by nk? Abelian group. What is subgroup generated by n comma k? Any linear combination, integer linear combination of n and k. So these elements are exactly or the form an plus bk. So because these are equal, this must be an element here, which means this is this form. Because these one of these elements. So business identity also follows from that proof, that cyclic subgroup, right? I think it also it's exactly the same thing, just that you consider ideals instead of ideal. It's exactly the same thing. You have questions. Okay, so from so the implication again, let me write it. So you have GCD of okay. So what does this tell you about the subgroups of Z? If I use that subgroup lattice notation, what does this tell you about the subgroups of Z? What are all the subgroups of Z? Yes, if you take any divisor of Zn, definitely that will generate some subgroup. In fact, any element of Zn generates a subgroup, but specifically, a subgroup can be written as being generated by a divisor of n. Why? Because of this. This is a divisor of n. So whatever element you take, the subgroup with that, the cyclic, they are all cyclic anyway. So you just have to consider subgroup generated by one element at a time. So if you take one element and generate the cyclic can be written as generated by a divisor of n. Okay. So if you take all the different devices of n and generate cyclic groups with them, those are the only subgroups you will get, right? Now suppose yeah, okay, suppose D1 and D2 are two different devices of Zn, such that let's say D1 divides D2. Then what's the relation between the subgroups generated by them? In which subgroup generated by D2 will be smaller, right? Because if you take a larger element and generate subgroup, larger divisor and generate subgroup, you will get a smaller subgroup because it will reach n faster when you multiply, add it to itself. So this is that clear too? Like we'll take a concrete example. See, so suppose I take Z12 and I say take say devices only. So I'll take 3 and 6. Okay. The subgroup generated by 3 will have what elements? 0, 3, all the multiples of 3. So 0, 3, 6, 9, and that's it, right? 12 is an external 0. Whereas subgroup generated by 6 will have only 0 and 6. This is contained in this. So when you take larger divisor, it will reach n faster when you take the multiples, right? So you get 2 elements. And this is and also because this is a anything which is a multiple is a multiple of this. Means all these elements have to be here, right? Should not point. So yeah, all these elements have to be here. So that's why this you get. So what does that tell you about the subgroup lattice of Zn? If you read the part about lattices, so you take subgroup generated by 0 will be 12 subgroup. Subgroup generated by 1 will be the whole group. Okay. If you take, let's say, prime number, prime divisor of n, say p, will be any other subgroup that contains this one? Will any other proper subgroup contain this subgroup generated by p? No, because it would have to be a divisor of p, right? By this, it would have the converse. So if it would have to be a divisor by p, so you cannot, right? So okay. Similarly, if you take some other prime q, any other prime factor q, so pq, I'm not writing that. Okay, that will also be like this, and these, yeah, because there's nothing else in between. Right? Now, if you take some other divisor, like suppose for example you take pq. PQ is also one of the elements. Let's say it is not n, so not 0, something like this. It will be contained in both of them. Correct. So basically, you get this lattice structure. Fine. So this will be, what will you get here? What will be the subgroup, which is minimal? This is called minimal subgroup. These are called maximal subgroups. Okay. What are the minimal subgroups? That means they are non-trivial subgroups without any proper non-trivial subgroups. Okay. So what will that be? One of them. This is subgroup generated by P. This is subgroup generated. You want to take largest possible n by P. Okay. N by P prime n by P correspondingly. Similarly, n by Q. Sorry, n by Q. Actually, I should write it the other way. N by Q here, because n by Q will be contained in subgroup generated by P. Why? Because when you divide n by Q, it is a multiple of P, right? Similarly, n by P will be contained in this. Okay, there are some other things in between possibly, so that's why I'm not straight edge. Okay. And so on. Okay. Similarly, n by pq would be there like that somewhere. Okay. Whereas, so again, if you write the part lattices, if you take let me call D of n the set of positive divisors of n, and you take the divides relation. This is a partial order relation. Partial order relation, if you recall, it's a flexive, transitive, antisymmetric relation. So any positive integer divides itself, correct? If a positive integer divides another one, and that one in turn divides this one, what can you conclude? If A and B divides A must be equal to B. That is an antisymmetry. And if A divides B and B divides C, then A divides C. That is, B is a multiple of A, C is a multiple of B. So C is a multiple of A. So it is this is a partial order relation. So the set of all positive divisors of n together with the divides relation is a poset. Okay. What will its Hasse diagram look like? So if you read the appendix, Hasse diagrams are explained there. What does the Hasse diagram look like? What is the largest element? Meaning everything else is n. What is the smallest element? One. One divides everything else. Okay. P is a prime factor of n. Then where will you draw it? So 1 divides P, correct? Yes, 1 divides P. Anything else exists between 1 and P that divides P? No. Something divides P, it has to be P or 1 only. Right. Similarly, 1 divides Q. P and Q both divide what? PQ. And again, nothing else can come in between them. Right? Similarly, if you want something just below n in the set, what will that be? So not n minus 1 because it has to be a divisor of n by p, for example, right? So n by p will be just below n, n by q will be just below n, and so on, right? And p will divide n by q because p is q will divide n by p. Maybe there are so many things in between possible. Okay. So what do you see? There is a one-word correspondence between this and that, only that somehow the order is inverted. This corresponds to this. This subgroup generated by P corresponds to this, and so on. Okay. So there is an anti-isomorphism of partially ordered sets between this poset, which is set of all positive divisors of n, and this poset, which is set of all subgroups of Zn under the inclusion relation. Okay. And both are lattices. So it's actually an anti-isomorphism of lattices. Okay. In other words, you have the dual of a lattice where you just take the relation and reverse it. So if A is related to B, in the new relation, you say B is related to it. That's all. So then that they will be isomorphic lattices. Okay. Fine. So that's also one of the. Okay. Actually, I solved one because of your example. G is equal to set of all complex numbers Z such that Z power n equal to 1 for some positive integer. Positive integer n. Okay. For some n in n. Okay. So is G cyclic? No, it is not cyclic. How do you say that? It can't be. Okay, you can't find a gen. If you assume that one of these generates, then for example, if you assume that Z power, not like that. If you assume that some Z generates for which Z power n equal to 1 for a fixed set. So suppose that G is actually this, where so z some z power n has to be 1. Then we take some w such that w power 2n is equal to 1 and w power n is not equal to 1. Okay. Then this w cannot be generated by that z. So yeah, you can prove it. I mean, I don't need to argue that carefully, but that's basically it. Yeah, so it is not cyclic. What is infinite? We already saw. Periodic. Yeah, that also we saw. G is periodic. Okay. So these questions actually taken from some earlier question papers because they are some good problems, but I modified them so that instead of the correct option or something, that just questions. Okay. So this was one of them where you had to choose the correct statement. So I think G is periodic. Again, they may not use this terminology, that periodic and so on. They will just say that every element of G is finite order. I just condensed using terminology because you should be familiar with the terms also. Okay. In most cases, they will the statements. Second one, can a group G have a proper isomorphic result? Just think of it and say, right? Is there a group G? Can you think of a group G which has a subgroup isomorphic to itself? Okay, Z is an answer. What are the subgroups of Z? That's another question, I think. All the subgroups of Z are of the form NZ or N not. So if you take non-zero N, that will be some 2Z, for example, is isomorphic to Z. Okay. Yeah. This is just there are others also. You can think of other such examples. Oh, yeah, that is the next question. So we already answered that. So for G is a finite cyclic group. For any group H, so G is a finite cyclic group. Okay. Show that for any group H, homomorphisms from G to H are in one-to-one correspondence with elements H belonging to capital H, such that order of small h divided order of G. That means in this case order of G is n. So I want to show that this is uniquely determined by. So this corresponds to some H in H such that order of H divides n. Okay. So to think of what are homomorphisms from a cyclic group, what will they look like? So you take, let's say, you can take it as Zn if you want. So what are the elements of Zn? 1, 2, etc. and minus 1. Now you take any homomorphism from this to some H. Okay. These elements have to map somewhere. For example, 1 has to map to some element H. Now, given that 1 has mapped to H, where should 2 go? H square. 2 has to go to H square. Use multiplicative notation. Okay, here is additive notation. I'll use multiplicative notation there. So 2 has to go to H square because, yeah, f of x plus y, because this is additive notation, has to be equal to f of x, f of y in H. We use multiplicative notation. Okay. Because of that, 2 is actually 1 plus 1. So f of 1 plus 1 has to be f of h, f of h. I mean, f of 1, f of 1, which is h square. Right. Similarly, 3 has to map to h cube, so on. K has to map to h power k, n minus 1 has to map to h power n minus 1. So you only have the freedom when defining the homomorphism f, you only have the freedom to define what f of 1 is. Once that is determined, everything else is determined. Conversely, where all can I map 1? So this is given f, I can find this h, and I say that f is completely determined by the image of that. Conversely, I want to now define freely some homomorphism. What can I map 1 to? What all can I map 1 to any element of h? That is a question. So for example, from Z3, let's try. I want to map from Z3 to let's say Z4. Okay. So I will map 1 in Z3 to let's say 2 in Z4. Will this work? So Z3 has element 1, 2, 3. So 1 will map to 2. I am trying to do this. Okay. 1 will map to 2. Here use addition on both sides, not multiplication. Addition on both sides. 2 will map 2 plus which is 0. 3 will map to 2 plus 2 plus 2 which is 2. That's okay. Then 0 will map to 4, right? 4 is 0. So 0 plus 0 plus 0 plus 0, which is oh, right. Not this. It's yeah. In fact, that's a problem. Sorry. I'm taking Z3. Yes, that's exactly the problem. 3 is 0. Okay. 3 is actually 0 only. Z. So 0 maps to 2. Is that the problem? Because we know that homomorphism must preserve identity. 0 must map to 0. So why is this not working? So this is order. This one has order 3, right? So after 3 movements, like if you add it to itself, after 3 steps it will be back to 0. In the other side also that must happen, right? So if you map it to some element, order is not compatible with, but order is not compatible with, that means here what happens, the order of 2 is actually 2. It's not larger, so it's not that you're not reaching 0 fast enough, but order is 2, which is smaller, still it doesn't work. Because here it's something like you are traversing a triangle, whereas on the other side you're taking 2, so 2 is just 2 things, right? So in 2 steps you must get 0, but here only in 3 steps or multiple of 3 steps you will get 0. So you can't write 2 as a multiple of 3. No problem. So what must the condition set? If you write it down exactly, then multiplicative notation itself I'll write. Observe that we know that f of f of x power n is equal to f of f of x whole power n is equal to f of x power n, but f x power n is 1, so this is f of 1, which must be 1, right, in H. So whatever you do, f of x has to be some element such that power n is equal to 1. Does that mean its order is n? Not necessary. It can be multiple of divisor of n. Which order? Yeah, correct. Divisor is correct. Divisor of n. Yes. Yeah, order is a divisor, smaller, right? So order of f of x might be n or any smaller number which divides n. Okay. So that's what. So that's right. And any such h will work because there is nothing else that goes wrong if you do this. So therefore, there one correspondence between elements of h such that it divides n, that is order of g, and the homomorphism from G to H. Okay, this is a useful property to know. It's actually more. It's actually true in other settings also. For example, if you have a group generated by 2 elements x and y, maybe satisfying some relation. So, for example, let's take a moment to write this out. Do you know presentations of groups? Defining a group by a presentation, not representation, presentation. Okay, so you have seen this, but I'll tell you if you don't know the name. So I can write dihedral group as of degree n as we can define the dihedral group like this. What does this mean? It is generated with two elements satisfying the relations that r power n, so r and s are the letters, r power n is equal to 1, s square is equal to 1, and rs is equal to sr inverse, or equivalently rs is equal to sr power n minus 1, because you can see that r power n minus 1 is r inverse. Okay, so sr n minus yet another way of writing it is srs is equal to r inverse, or r power n minus 1, or srs inverse is equal to. So you recognize that srs is actually srs inverse, which is conjugate of r, because s inverse is s only. Okay, so just recognize it. When you conjugate r by s, you get its inverse. That is the main thing to remember when dealing with the dihedral. So this is the dihedral of degree n. Order is 2n. So some books actually write d2n. But if you're considering it as a permutation acting on polygon, so it's more sensible to write the degree, because if we write, what is S6? Is it the symmetric group of order 6? No, it is degree 6, order 720. S3 is, so right here, whatever notation. Fine. So how do you now get the group elements if you are given the presentation? It's not an easy, there is no easy answer for this. I mean, there is no algorithm that can always exactly tell you what, even if it happens that this is a finite group, that's also not clear. From this presentation, it is not at all clear whether the group is going to be finite. We can say the generators are finite elements, but finite, that does not guarantee that the group is finite. You can have, okay, we'll see that in a later question. But it may be finite or infinite. There is no algorithm that in general can tell you this. But here anyway, you know it. So you can actually try and you will get the answer. Okay. So I mean, cases that you can actually try to get it and then you will get it. There are other cases where you can't. So here what you do is you try to write all possible products. The meaning of this is you try possible products of R and S, right? Like R, S, R square, S square, which is 1. So 1 means identity. Okay. Then RS, then RSR, RS, R square, and so on. I'm not writing statically, but if you systematically write down all possibilities, but then you use the relations to reduce what you have. So for example, when you write RSR, using that, you can write this as R inverse S. Okay. Actually, this implies immediately that SR, so from here, implication is SR is equal to R inverse S by just using inverse. Okay, so you can write this as R inverse S, which is just S. So RSR is equal to S. Similarly, whenever you write a big word, you reduce it, and in fact, you can of this relation. Because of this relation, you know that every element can be written in R power I, S power A. And what are the values of I that you need and J? Because R power n is 1, you don't need to consider all infinity which is I. You can just take I between 0 and n minus 1, J between, I mean, J equal to 0 and 1 because S square is 1, right? So it follows from particularly this relation and then these two, the element can be written in this form, because you get a big word like many R and S and so on, you can always go on using this to separate R and S. And then you get a power of R and power of S. That can be reduced using this. Okay. Yeah. So it follows that it is this. Okay. Under these conditions, but of course satisfying the multiplication as defined by this. So that multiplication using this. Fine. This is called defining a group by a presentation. Okay. Actually, it comes from free groups. The theory is that what is called a free group generated by R and S. Whatever generator, what the names don't matter. So if you take free group, so-called of rank 2, generate R and S. This is a set of really all such words. Okay, so there you have some R power I1, S power J1, etc. R power I, let's say IN, oh, not this N, some R power IM, S power JM for I1, etc. IM and J1, etc. JM in Z. Okay, and itself in 0. Okay. So all the words, if you have letters, then it's more complicated. Like, right, more complicated expressions will be there. But you can always say J1, J2, and so on to be 0 also. So everything possible can be obtained. If you want to end in R, not S, just take JM to be 0. So that's fine. But in Z, so inverses are also there. Okay. So these, then that can form a group under multiplication defined by just concatenation. You just concatenate the elements, but with the rule that if you get something like X and X inverse next to each other, you cancel them out. So use that rule when multiplying. So that will give you what is here free group generated by 2 elements. There will be a quotient of that. You don't have time to go into that, but really the group presentation, you start free group quoted by certain normal subgroups generated using these relations. So that will give you this. So any finitely generated group has such a finite presentation. Any group has a presentation. Some groups are infinitely generated, not finitely. But any group can be written as a quotient of a free group of appropriate rank. So here this is a group generating elements. So write it as a quotient of. Okay. So the point is, now suppose you want to determine homomorphisms from Dn into some group. So given this presentation, question is, what are the homomorphisms from Dn into some arbitrary group G? So this will represent the collection of homomorphisms from Dn into G. Okay, this is just the set of homomorphisms from Dn into G. How can you determine these? That's the question. We already did this for this, right? So where was it? Right here. So we already did, if I use this notation, we already determined this. Okay, these are determined by elements which have order dividing order of n. I mean order dividing n. So in this case, what can you say? There's no very nice answer that way, but using this you can see. So what you can do is see, if I give you a particular homomorphism f, then again similarly what we did here, right? Here we said that one has to map to something, but once you decide where one maps, then 2 has to map to that element square only. 1 has to map to some, 2 has to map to h square, 3 has to map to h cube, and so on. So once you determine where 1 goes, everything else is different. Similarly, what can you say in this case? R and S, because as soon as you decide, say R goes to some X and S goes to some Y. Now you already know that every element can be written in the form R power I S K. So this has to go where? X power I, Y power J. So every homomorphism from Dn is determined by these two images only. So you just have to say where R and S. But what freedom do you have in this? Can you map them to any two elements? No, because these relations also hold. So previously we saw, because one has order n in Z, whatever you map it to, that must also have order dividing it, because it must be one, right, dividing it. So similarly here, one thing is x power n has to be 1. Similarly, y square has to be 1. What else? This also must be satisfied. It's also true that xy must be equal to yx inverse. Okay. So if you, conversely though, if you map it to any element x and y that satisfy these equations, that is guaranteed to be a homomorphism. Okay. So if you want to determine all homomorphisms from a group of this form to any given group, this is how you count. This is how you describe them or list them. Okay. You just have to ensure that the equation is satisfied. So if you have some group, and if you know the presentation of the group, then you can use it for determining all the homomorphisms. Okay. In particular, if you want to determine automorphisms of the group, so then these x and y will be there here itself. Okay, so automorphisms of the group you can determine, endomorphisms of the group you can determine, and so on. So in that case, if you want it to be bijective, then you have to do some additional work. You have to make sure this defines an injective mapping or whatever, right? That is extra work, but basically homomorphism determine like this. Okay. So that Hom GH form group under pointwise multiplication of homomorphisms. So very quickly, let me dispense with this so that we can go to the next question, which is more interesting. So what are the elements of Hom GH? Some say F1, F2. These are actually homomorphisms. Now, what do we mean by F1 group under pointwise multiplication of homomorphisms? Pointwise multiplication means I'm going to define F1 dot F2 as what? Dot F2, I need it to be a binary operation. That means F1 dot F2 should also be in the same set. Means it should also be a homomorphism from G to H. First of all, it should be a function from G to H. So how do I define it? Pointwise multiplication means I simply define F1 dot F2, not composition. Okay? Composition is not defined unless H is equal to G. So I can't do that. So it is F1 dot F2 of X I define to be pointwise multiplication. Okay. F1 of X dot F2 of X, where this multiplication happens in H. F1 of X and F2 of X are elements of H. So define this. Okay. Right. So now this is a function. No problem. Is it a homomorphism? Is it a homomorphism from G to H? It's a function from G to H. So check the homomorphism. So let me call this H. Okay, let H equal to F1, F2. Okay. Just to give clarity. So if I take X and Y in G, is it true that H of XY is equal to H of X, H of Y? Let's just evaluate LHS RHS separately. That's it. H of XY by definition is F1 of XY, F2 of XY. Any further reduction possible? F1 and F2 are homomorphisms. F1x, F1y, F2x, F2y. Okay, that is elements. Fine. H of x, H of y. That is H of x is F1x, F2x. Okay. And H of y is F1y, F2y. Are they equal? Why not? Two elements are interchanged. It is given that G is abelian. It is not given that H is abelian. It is only given that G is abelian. So what? You can prove it using elements, or you can think of isomorphism theorems. Isomorphism theorem tells you that image of G is or G modulo kernel of F is isomorphic to image. These elements are in the image. Any quotient of an abelian group is abelian. That's all you need. You don't need H to be abelian. This image is abelian. If you don't like the proof, you can use elements to prove it. We know that in G, xy is equal to yx. So f of xy is equal to f of yx because xy is equal to y. But f of xy is f of x, f of y. F of yx is f of y, f of x. So f of x and f of y commute for any x and y in G. Right. So image of an abelian group under a homomorphism is abelian. That's all we need. You only have elements of the image, not arbitrary elements of H. So these definitely commute. So these okay. Is G abelian? It is abelian. So this is a homomorphism. So it is closed under that. Now that's okay. What is the identity mapping? Not identity mapping, identity element of this. Identity mapping is not defined because it's G and some H. So you can't talk about identity mapping. Trivial homomorphism. Trivial homomorphism, let me call it epsilon 1. Okay. Epsilon. Okay, that's okay. 1 maps x to 1. Because the projection is like this, right? I want after applying F1 and that, I get F1 itself. That means this element should be identity element of H. That's so yeah, this is going to be identity of this, and inverse. What is inverse? If you have F from G to H, define, I'll say F bar as X maps to F of X inverse. Okay. Is that a homomorphism? You know that the mapping of element to its inverse is an endomorphism of an abelian group. So you can consider this composition of F with that endomorphism. So therefore, it's a homomorphism. Or you can explicitly verify. Again, you will have to use the fact that G is abelian. So because of that, it is. So FF bar is definitely going to be F1 because F will map X to X. I mean X to F of X. F bar will map the same X to F of X inverse. Fx inverse because F is homomorphism. So when you multiply them, you will get trivial, I mean identity element, which means FF bar is epsilon. This is a group under pointwise operations. Okay. So G is abelian. Another possibility is there. If H is abelian, then I think it is sufficient if H is abelian also separately. Right? G is not abelian, H is abelian. That's enough. That's enough. That's all you need. So you only need image should be abelian. Okay, fine. So next question. Prove that that's a question with the correction. I typed the wrong one. So form Z is isomorphic to G. All homomorphisms from Z to G, group under multiplication or addition, whatever. It's isomorphic to that group is isomorphic to G itself. Whatever group G you take. How to prove this? All the ideas are already there. Just take it and try. Yeah. Huh? Yeah, Z is abelian, so this is definitely a group. Okay, so how do you start? You start from G or this side? You want to get an isomorphism from this to that or this that to this? From the G to G. Okay. So if you take F in form ZG, I need, so I am trying to define a mapping from ZG to G, and I need this phi to be ultimately a group isomorphism. Right. Okay. So in phi, I need to say where this goes. So what is phi of F in G? What is phi of F in G? How will I define phi of F? Again, use the fact that from we did it for Zn, but obviously the same holds for Z. Easier. What is it? What is the order? Z. Infinity. So there we had the condition that if you want homomorphism from Zn or cyclic group of order n, Z to H, then you need to map 1 to elements of H that have order dividing this order. But here the order is infinity, so that condition goes away. You can take whatever order you want. You will never run into problem because that 1 into 1 plus 1 plus 1 plus 1 never becomes 0. So you can map to any element of G. So the idea is there is a one-to-one correspondence between this and this. That is already clear. We just need it to be an actual group isomorphism. Okay, that's the only thing. Fine. So F of 1. The key thing there is that determines the homomorphism. So F of 1. You take F of 1. Okay. Take F of 1. So that this is a isomorphism. It is definitely well defined. No question about that. And yeah, both are groups. Is it a homomorphism? That is the main question. To take shall we use additive notation here because Z is written under addition, right? So we'll use additive notation for G also. So I'll take phi of say F1 plus F2. Okay. This is by definition F1 plus F2 of 1. Okay. By definition, what addition we have defined for or multiplication in the case, that is by definition pointwise. So that means this is defined as, we are not proving this. This is defined as this. Okay. That is of course phi of F1. This follows by definition. The only thing definition makes a group or not is the only question. So by definition, this follows. It is phi of F1 plus phi of F2. Okay, so it's group homomorphism. Fine. Not convinced. Yeah. It is a group homomorphism. Kernel. What is a kernel? So f is in kernel of phi and only if phi f, which is actually f of 1, is equal to identity of, okay, I'll write that also 0. Okay, 0 of g. Okay, g also you consider additively just to make the condition consistent. So that should be 0. But if f of 1 is 0, what is f of n is f of 1, etc. So the point is, once you determine, as we noted before, if f of 1 is equal to some g, then f of n, which is f of 1 plus etc. 1 n times in z, this is equal to n times f of 1, which is n times g in g. Okay, that is the point. What we did before. Okay, I'm using additive notation, right? And every element z is some n, right? You do this with minus n also, like negative integer also, similar thing, just minus 1 and so on. So this implies, I mean, this is if and only if f of n is equal to 0 g for all n and z. That means f is the trivial homomorphism. Just write it as epsilon naught. Okay, trivial or zero homomorphism that maps everything. So the kernel is trivial because that's the identity element here. So the kernel is trivial. So it's surjective. And it's surjective because the order divides doesn't apply here. So you can choose whatever element of G you want as f of 1. If you want a particular homomorphism that maps something like in G. So if I take G in G, then definitely there exists a homomorphism here such that 1 maps to G. So therefore it's surjective. That's why it is isomorphic. Okay. This is a very small version of some implication of unit lemma in characteristic again. Okay. Fine. So I go ahead because we don't have that time. And I can't do group theory again tomorrow. So we finish today. So to the first one, G is a finite group which are following your R2. First one, if G is in G, I mean, if an element G of G has order M and divides M, then G has a subgroup of order M. Is that true? Subgroup of order? Oh, I think I inverted. So G order of G is M. N is some integer dividing. Is that true? We are not saying that N is the divisor of order of capital G. N is the divisor of the order of an element of G. Order of an element of G. What is the a cyclic group? So the question is asking if you have a divisor of the order of a cyclic group, is there an element in that cyclic group with that order? Yeah, you can just take G power and divide it by that. It is true. So, I mean, I guess the intention is to trick you into thinking that you are asking for converse of Lagrange theorem, which is false. But this is not that, because it's group, you're only thinking of subgroup generated, cyclic subgroup generated by G. Okay. In fact, converse of Lagrange theorem is true in, yes, infinite abelian groups, right? Not only cyclic groups. In any finite abelian group, converse of Lagrange theorem is true. Okay. Whatever divisor you take, you can use fundamental theorem of finite abelian groups or something. You can do that. Here in particular, okay. Multiple claims are possibly true in this, so I'm going to explore those. So, if SL of G, it's only the first claim. SL of G is a chain. Again, this is the language in the original question. I've just rephrased it into terms we have studied here. So, SL of G is a chain. It means what? In a lattice, chain is so you have some lattice L or poset L. Yeah, generally in a poset also, a chain is elements which are related like this. Okay, x1 is related to x2, x1 less than or equal to x2, x2 less than or etc. xn. That means any two elements are comparable. So in the lattice like this, B and C are said to be incomparable because neither B divides B less than C nor C less than or equal to B according to this diagram. But A and B are comparable, B and D are comparable, A and D are comparable because this indicates it's related to D. So this, for example, is a chain in lattice. Okay, or if lattice itself is an chain, system of D is a chain. The G is cyclic, true or false. That is the subgroups. Okay, so again, translating into more simple words, if you take all subgroups of G, whatever, maybe finite or infinite, just given that it's a finite, yes, of course. So if all the subgroups of G actually form a chain, that means you don't have any subgroup like this. You don't have any subgroup where neither H2 is contained in HK nor HK is contained. So that is not there. Any two subgroups contains the other. Two subgroups you take, one of them contains the other. So does that imply this is a finite group is given. Power of? Yeah, actually something stronger is true. Order of G has to be some power of P. Why is it? Okay, any subgroups order must divide order of G, that is true. Because given that it's chain, that is true. But can I say that if the order is not a prime power, then there will be a subgroup of that? What is Cauchy's theorem? Several theorems in general. One of them is Cauchy's theorem. Cauchy's theorem tells you that for every prime factor of the order of a finite group, there is an element or there is a subgroup of that order. In fact, Cauchy's theorem tells you there is a limit of maximal power of that order also. But in particular, you have P and Q are two groups. Two different prime devices. Okay, two different prime devices of order of G. Okay, then you will have two subgroups, let's say HP and HQ, orders. In fact, those two elements of those orders. So that, okay, can any of them be contained in the other? Can either of them be contained in the? No. So this cannot happen. Therefore, this group is of prime power order. That is true. Then what? How does it make it cyclic? This is one way. I'll tell you another way to prove this without considering this. This is a little bit of you're using some results. Without that also you can do. But yeah, this is anyway definitely what I first thought. So if you think along these lines, it is true that G is has some prime power order. We don't even know if it's abelian. P groups are there of, I mean non-abelian P groups are there as well. What makes it cyclic? Hmm. Yes. So those will be incomparable. That is true. So if you know that it's abelian, then again you have to use another big theorem, which is fundamental theorem of the abelian groups, finite abelian groups, and tell that they have to be direct products of cyclic groups. In this case, cyclic groups of different prime power order of the same prime, different powers. Okay, so any two of them, if you take two different ones, because direct product, they will be neither will be contained in the other. Okay, that is one way. But again, for that you need to get abelian in the first place. Even if it's non-abelian, suppose you have two actually that boils to an argument ultimately, which does not use the order. So I'll tell you a simpler argument which does not use any of these results. We know that G is finite. So it has some finite generating set, maybe the entire set itself. G can be generated by all its elements together, right? Suppose, for example, that can this happen? Neither x1 is contained in the subgroup generated by x2, nor x2 is contained in the subgroup generated by x1. Is this possible? No, because then you would have x1 is not contained in x2, x2 is not contained in x1, so they won't be part of the chain. They won't be part of one chain. Right? This is true. Neither is contained in the other, correct? Because this is true. Can I say it is true if and only if? Definitely, this would imply that. Right? Is it true? Similarly, the other. So one of them has to be contained in the other. So this both cannot happen. Without also generality, let's say that x2 is contained in cyclic subgroup generated by x1 without loss of generality. Okay, one of them this is not possible. It's a contradiction, right? So without loss of generality, x2 is contained in this. So what can I do now to the generating set? Let me rewrite this. This is a generating set. In fact, I can take all the elements, but so that is a guaranteed generating set. But let me take any generating. Start with any generating set. Okay. Now what can I do here? If x2 is there, then do I need it as a generator separately from x1? No, because x2 itself is a power of x1. I don't need it separately. This is equal to this. Now, repeat the argument. By induction, you will get it's equal to, again, without loss of generality, if you assume that every time x1 is the more powerful one, ultimately you will get x1. Okay. Clear? Yes, because otherwise this process won't terminate. Okay, you want a counter example? Yes, proof for P group. Proof for P group. Proof for P group, they do form a chain. Okay, in proof of P group, you have one is of course 0. Okay, or if I write in that complex roots form, then 1 is there. Then let's say P is equal to 2. Proof for 2 group I'll take. Okay, so the square roots of 1 are 1 and minus 1. Square roots of these two are 1 minus, or fourth roots of 1 are 1 minus 1, I minus I. Then eighth roots and so on. Okay, this will be the chain. They will all be, if you take basically in that group, remember our group was Z belongs to C such that Z power P power N is equal to 1 for some n where p is a fixed prime. So if you take a larger n, you will get more roots, but those roots are also what? Like if m divides n, then m divides n. No, m is a multiple of n. Say m is a multiple of n. Then mth roots are also nth roots, correct? Like fourth roots are also. Sorry, the other way. The other way. Yeah, m divides n is correct. M divides n, then mth roots are also nth roots. So square roots are also fourth roots. They are also eighth roots, and so on. So this containment will be there in that. So that you have an infinite chain. Okay, but the group is not cyclic as we already saw. Right? So finite is required. Yes. Yeah. So A and B are both true. C, if G is cyclic, then SL of G is a chain. Is it true? Definitely not. Consider Z6. If you have any cyclic group, we already said it has to. In fact, for this to form a chain, you have to have that prime power order. Otherwise, it won't work. So definitely C is false. It need not be that SL of G is a chain. D, if for each positive integer m dividing order of G has a subgroup of order m, then D is abelian. Is that true? Yeah, just consider the smallest non-abelian group, which is immediately a counterexample. You have in S3, you have S3 which has order 6, you have subgroup of order 2, subgroup of order 3, and of course 1 and 6, right? It is not abelian. So yeah, A and B are true in this, other two are false. True or disprove? In Sn, any two elements are conjugate if and only if they have the same order. Not true. You have to know this only. I mean, you can derive it with some difficulty. It's not very simple, see, but yeah, why? Okay. Hmm. Okay, like that. Yes, that is true. 1, 2, and 1, 2, 3, 4. Okay, in S4. These both have order 2 because they're, yeah, but they are not conjugate. What is the condition for two elements in S4? Cycle structure, which means in the cycle composition, when you write, if you write cycle decomposition, these are the cycles: sigma 1, sigma 2, etc. Sigma k are the cycles, and then this has length L1, this has length L2, and so on. Lk. Another one is say mu 1, etc. mu k. First of all, it should have the same number of cycles, and under some reordering, this also must have same lengths. Okay, basically, set of lengths here. The multi-set of here is the same as multi-set of lengths here. If and only if this is true, then the level conjugate in Sn. In Sn, okay. In a subgroup Sn, it may not be conjugate, right? So this is not difficult to see. So, for example, I have 1, 2, and let's say 3, or let's take slightly bigger. 1, 2, 3, and say 3, 2, 4. Okay. I want to write 4 as a conjugate of 1, 2, 3 in S4. What element should I conjugate by? What is that element by which I should conjugate? Simply, this here in place of 1 I need 3. Here in place of 2 I need 2 only. Place of 3 I need 4. Just write that down. 1 goes to 3. 2 goes to 2, so don't write it. 3 goes to 4. 4 goes to Where is it? No. Actually, if I write like 4 is here, fixed, right? Here, 4 is here. What is fixed there? 1 is fixed. So 4 goes to 1. So close it there. Fine. That's it. Three goes to 4. It will not read. See, it will not in place of 3. What do I have? 4. So let's look at in each place what am I replacing it by, and just write that permutation. Actually, it is like if I write down what are the mappings. So this is my conjugating element. Let's say it is sigma. Then I write sigma of 1 here. It is 3. Sigma of 2 here. It is sigma of 3 here. It is 4. And sigma of 4. 4 is fixed. So sigma of 4 is 1. Because what is the fixed point here? Which is not written, but it's there. That is 1. So sigma of 4 is 1. Doesn't matter because disjoint cycles commute. You mean in this permutation or that permutation? Or this side or that side of the cycle? Yeah. No. It is not position wise. So if you have multiple fixed points here and here, whatever you want to map to whatever. Doesn't matter. Okay. You get that permutation. That's it. Okay. So when you will get that. Okay, very later. But that's it. In other words, if you are conjugating by sigma, so if you have a cycle which you are conjugating by sigma, so let's say this is some these are some elements I1, I2, etc., IK. If you're conjugating, so you can conjugate individual cycles separately, right? Because if you have a product, conjugate of product is product of conjugates. Those commute. Those operations commute. Product conjugates. Just cycle, just conjugate each cycle separately. So here you get sigma of I1, sigma of I2, etc., sigma of IK. That is how you conjugate. Okay, it is just mapping that you can verify later. Fine. So this is not true because these will not be. It's known. This is true if and only if they are conjugates. Third problem is related to this. If G is a finite group, then for any two elements x and y, order of x equal to order of y. If and so x and y are elements of a finite group G, claim is order of x equal to order of y if and only if h inverse equal to y for some h in H for in some over group of G, in some larger group, not in G, that is already false, we know. But in some larger group, you can embed G into some larger group in which these two elements will be conjugate. Is that true? We will stop after this one. Okay. Is this true? And because the question is so elaborate, it must be true. Huh? One conjugate elements have, that is definitely true. Any two conjugate elements in whatever group will have same order. This is why in all these questions that order is mentioned, because if it was not mentioned, you can obviously say false. So your order condition is true. This is true. Like I said, it must be true because some elaborate construct beyond. And with answer. In fact, okay, it's not easy to guess. So I'll just tell you how to get this. What is Cayley's theorem? Any group is any finite group, it is isomorphic to a permutation group. Permutation group means a subgroup of Sn. Which in the proof, if you see which permutation group you get, or which Sn do you get? Permutations of G. So let's say order G is equal to n. Then what you do is you define an action of G on the underlying set of G. Underlying set because it does not preserve the group structure or anything. So underlying set of G as G dot x equal to Gx. Okay. This is the basic action. It's an action. 1 dot x is obviously x and g x is gh, which is gh dot x. Okay, so it's an action. And oh yeah, we'll discuss in group action. But again, we must be familiar with this. A group action on a set. So I'll just write it down without proving anything. If you have a group action on a set, then that is equivalent to a homomorphism from G to the group of permutations of X. Why? Because here what you're doing is corresponding to every G comma X, you get this G dot X in X, correct? So what you do is you define G going to, let's say, some pi G, which is defined as follows. Simply that. Okay. But pi G is function from X to X. That is obvious. Okay. Because you take an X, get G dot X is also an element of X. Is it a permutation? Yeah, because you can cancel it by G inverse. So the inverse exists. Pi G inverse, observe that pi G after pi G inverse equal to the identity function of on X. So it is definitely a permutation. So corresponding to G, you get a permutation of X if you have a group action. Is this mapping phi a homomorphism? Yeah. So observe that. So if you take phi of GH, this is pi GH. That's in fact pi G composition pi H, because GH does what? It maps X to GH dot X, correct? And this does what? It maps X to H dot X, but then pi G maps X to G dot that. But by this axiom, I mean by the second axiom, GH dot X is G dot H dot X. So this mapping is a group homomorphism. Okay. So therefore you get a group homomorphism from G to symmetries of X, permutations of X, whenever you have group G acting on X. And this has a kernel also. Okay. This kernel of phi is called the kernel of the group action. And if that kernel happens to be trivial, then you call this group action faithful. Which means what? Kernel is trivial means what? Distinct elements of G define distinct permutations of X. No two different elements of G will permute all the X in the same way. Some elements maybe, but not all the elements in the same way. Okay. So this is in fact a faithful action. Okay. Because when will G dot X be equal to trivial? That's enough to check. When will G define the trivial or hybrid morphism? So G dot X has to be X for all X. So that will happen only if G is, in fact, if for one X if it is true, G has to be identity element. So this is a fatal action. Okay. So yeah. So when you have this, you know that G mod curve phi is isomorphic to what? Image of phi, which is a subgroup of sim of X. So in particular, when X is this will some n, this will be Sn. Okay. So here you have, using this, G mod kernel is trivial. So G itself. G is isomorphic to some subgroup of Sn. So in fact, I'll just write G is a subgroup of Sn. Okay. G is isomorphic to a subgroup of Sn. G is a subgroup of Sn. You can identify as a subgroup of Sn. Then, yeah. Now, you want order of x equal to order of y. Order of x equal to order of y. So now, consider x as an element of Sn, y as an element of Sn, and take an arbitrary element of yeah, look at its action. Okay, so in fact, we want to write down the cycle structure of x in Sn and y in Sn. So what is this? So you take x and y are acting on G only. No? So if you take any element G, what will be the orbit of G under this action under x? So you'll have G, then xg, correct? How do you write down the cycle structure? You take an element in the set and apply the permutation until you come to that. Then you take whatever element remains depending. Again apply it, and these give you the cycles. You start with any element G1, take any element G1 of G, apply x to it, you get xg1. Then you apply x again, you get x square g1, and so on. When you come back to G, only when x power n minus after x power n, only when x power n you reach, right? Because these have to be distinct elements, right? Because this is a multiplication in the group only. You are not acting on some set. Actually, this x and g1 are elements of G. So x, like if you write x power I g1 is equal to x power j g1, that means when can the, or more simply, if you write x power I g1 is equal to g1, what does it mean? X power I is equal to e. Right. So it can only happen when it's the order of x. So if you assume let's say so this is one cycle. If any element is left out, call it G2. So G2 will have cycle similarly. Also the same cycle, right? Same length. So all the cycles will have the same length. Similarly, if you take y and do this, so again you will get G1y, I mean G1, then y G1, etc. y power k minus 1 G1. Similarly, G2 will be left out. So you have to argue why G2 exactly will be left out. G2 is left out there. Okay. Again, basically cancellation. Okay. So they will have the same cycle structure. So this is the cycle structure of X. If you want, you can call it sigma X. Cycles the permutation corresponding to X in this embedding. This is sigma Y. So they have exactly the same cycle structure. So therefore, this Sn is a group containing G or a copy of G as a subgroup in which X and Y are conjugate. You should actually try this. This is very abstract, I know. Try this out with an actual group you take. Like, obviously, don't take S3 itself. Some take V4 and try this. Take line 4 group, embed it into S4. You don't have to write down all elements of S4. Just look at what happens when you apply elements of V4 to itself. Actually, it's very simple. If you take V4 as EABC, then so if you want, you can call this 1, 2, 3, 4 copies of S4. Okay. So A will map 1 to A. That is AE is equal to A. It's like A1 is equal to 2 when you consider it as elements of S or elements of S. And AA is equal to E. That means 2, 1. Similarly, AB is equal to C. AC is equal to B. So the element A of client 4 group V4 can be represented by this vessel S4. Similarly, B can be represented as, what will it be? 1, 3, 2, 4. They have the same cycle structure. You can try this out with some other groups. Okay, we will stop for today. Thank you.